Electroscopes. Is everyone ready? We're talking about electroscopes. My name has been redacted, so we're going by Ron Dorr. Ron Dorr's my name. We're talking about electroscopes. Okay. Next slide. Electro-whaaa? What's an electroscope, right? So an electroscope, super basic. Okay, it's a draft, right? It's a draft. We're all okay. It's not due today. It's a basic scientific instrument. So this is like, it's super, super basic. We first described like how to do this back in 1600 by this guy named Gilbert, I think his name is. It's like French in his book, right? But it's like, it's not very useful, to be perfectly honest. So like we use it in an educational sense, and that's about it. The whole point of it is you can detect an electric charge, and that's about it. Quick and dirty method. Does it have a charge? Yes or no, kind of deal. And it demonstrates the Coulomb's electrostatic force. Cool. Okay, how do we do that? A charge. So what is an electroscope? What's happening here? So a charged body brought near this conductive metal ball here will either attract or repel the electrons in this neutral system, either towards it or away from it, and that will separate the leaves, okay? We're gonna get into this, right? Next slide. So before we do anything else, we should just make sure that this actually works, right? Like before we do any experiments, we're changing all our variables, we're mixing things up, we just need to make sure it works. You gotta get the basics down first. So I have a little video here. So we can actually play this video. And we can see we bring the PVC pipe in and watch these two little leaves. These two little leaves here. See how they separate? So the PVC pipe never actually touches it. Also, notice the blue paint. Wow, that's some good color correction, let me tell you. So essentially what happens when you bring the PVC pipe down, the PVC pipe has a strong, strong negative charge on it. The negative charge repels all of the electrons in the system. And since they're repelled, they flow downwards away from the PVC pipe as far away as they can get. And that means you end up having a net negative charge on our leaves because we have all the electrons that were spaced up here flow down into the bottom. Now they're all concentrated down here. Similar charges repel. Since they're both negative, they're gonna try to avoid each other. And we can see the separation. So success. That's a big win. Okay. So now we can change some variables, right? So we can look at replacing those types of leaves, the things that actually separate, as well as like, how do we charge the PVC pipe? Like, that's not a trivial matter. How do you charge this thing? It's kind of strange. So we're gonna change, we're gonna use paper leaves instead of like aluminum foil. And we're gonna vary the amount of graphite on it and like see how that affects it. And we're also gonna try different materials to charge this using the triboelectric effect, I think. Yeah, thanks. Okay, methods. Okay, so we have to be consistent, all that good stuff, right? So we're gonna stroke it 5 times, easy, same force. We're not gonna touch anything. We're gonna make sure it's neutral beforehand, all that good stuff. Boring stuff. Great, so predictions. What do I think? What I think is gonna happen, right? You always have to make a prediction before you actually do the experiment, right? Otherwise it's cheating. So, oh my gosh. So I think the darker the graphite, the more they're going to separate. And that's because graphite is conductive, right? So if it's more conductive, more electrons can flow onto the paper or off of the paper, having a greater charge density, having a greater Coulombic electrostatic force repelling each other, and you'll have greater separation. So that seems pretty logical, right? It's all you need to know there. Graphite conducts electricity, so the electrons can flow freely. Okay? So that's a pretty solid prediction. I feel pretty good about that. Charging the PVC pipe, that I have no idea. I don't know how that works. But I do my own laundry. I do my own laundry often enough that I can tell you, without fail, whenever I pull this stupid microfiber like face cloth out of the dryer, it's always stuck to something. and you take it off and it goes, and there's sparks everywhere, and there's so much static electricity. So I suspect that this is going to have a ton of static charge, and we can transfer that onto our pipe. After that, the wool socks sometimes stick to things, but like not as often. And t-shirt, even less so. Okay, so what happened? All right, we ran the experiment. Let me remind you, this is a quick and dirty experiment. Quick and dirty, as in it doesn't really work. It's kind of the short answer of that. So the initial results showed that the lightly colored ones, the one with poor conductivity, separated the most. Sorry, these ones separated the most, and these ones separated the least. Well, that doesn't make sense, right? Like we had a pretty solid prediction. So what's going on there? So then I said, okay, let's do it again. And then now these ones are separating the most, and these ones the least. So it's like, okay, that doesn't make sense either. So what's going on? I'm having conflicting data. That's not good. I say, no way, Jose, cancel, get out of there. So I say, okay, obviously something else is going on here. So we need to reduce the number of variables we have. We're changing these leaves, right? I have 3 sets of these, and they're not exactly the same. So I change them out, and we get these results, where my camera's a little bit in the way. Oops. This one is slightly more separated than this one. So this is the dark one, and then this is the lighter one. So this is the result that we expected. Now, I suspect, as I try and move my camera back, okay, I suspect the reason for this is because you can see these holes. This hole is like closer to the top, and this one's further down. So when the leaves separate, they're not only fighting against gravity, but they're also bending the paper back. So the darker leaf has to bend more of the paper back, and it's more resisted compared to the lighter leaf, which has to bend less the paper back and can separate more. So by isolating or getting rid of another variable and using the same leaf twice, we're able to see the correct effect. We're able to see that. So that's pretty good. And then our prediction is also consistent with what we saw right at the beginning of the presentation, right? We had this cute little video where we saw what happened with aluminum foil leaves, right? I didn't even bring that close to 2 centimeters away, and it's separating more than these two. Those aluminum foil leaves are just like ready to go, super conductive. So it follows the same trend. Okay. Types of cloth. As predicted, our prediction was good, right? So microfiber gave the greatest charge, greatest separation, the wool second, and cotton third. And this makes a lot of sense too, right? Microfiber cloths are designed to have this property, to hold all this static charge. It's a synthetic material. You can't find this in nature. This is a man-made product designed this way. And you say, well, like, why would you want something to be full of static, right? Like you touch your hair and then your hair is sticking out. Like that seems kind of dumb. What would be the purpose of having this static having a static charge on a microfiber cloth? It's because it's for cleaning. You take this and you're trying to clean off the top shelf or whatever. It collects all the dust sticks to it because of the static electricity. It's contained in the cloth, and then you can go like rinse out the cloth or whatever. It's designed to attract all sorts of little bits of dirt and stick to it. It's the whole purpose of it. So of course it's going to have the greatest charge. And then we can also look at the triboelectric series, and then we can see that wool is more likely than cotton. We can just kind of look it up to give off its electrons. Cool. Now, there's a lot of things that I didn't like about this experiment. First, these leaves sucked. They didn't work. They didn't give me the results I wanted. They were super unreliable. Not very good. I'm gonna make myself really tiny for like 1 second. Second thing, it's really difficult to tell how far the leaves separate. So like maybe we can introduce some kind of scale like this. Also, the leaves rotated all the time. That was no good. So maybe we can fix them in place. Also, they're kind of heavy, not really good. Non-conductive guiding arm. Oh yeah, yeah. And then like you're bringing this PVC pipe, like I have it over here. You're bringing this PVC pipe in here and you're like trying to hold it at 2 centimeters in the same position. Like, I don't know, if I could just rest it on something and had a scale on it, that would be great too. And then like a good place to ground it as well in between each run. And that's it. Thanks guys. Science fact concluded. Can I mark that off? We're done? Done? Clap, clap, clap. Nice. Over and out. Over and out.